In section 2.4, we're going to study the derivatives of the trigonometric functions. And so we're going to be looking at functions like sine of x, cosine of x, and so forth to see what their derivatives are. In the case of the derivative with respect to x of sine x, that's equal to cosine x. The derivative of cosine x is negative sine x. Derivative of tangent x is secant squared x. Derivative of cotangent x is negative cosecant squared x. Derivative of the secant x is equal to secant x tangent x. And finally, the derivative of cosecant x is equal to negative cosecant x cotangent x. And so these are the derivatives of the 6 trigonometric functions. The same rules will apply for the trigonometric functions or expressions, such as the product rule and the quotient rules that we saw before. So with that in mind, let's take a look at these trigonometric functions and find their derivatives and other things about them. All right, for the function y equals 2 secant x cosecant x, we're going to differentiate that and find y prime. Okay, the thing to keep in mind here as we try to find y prime are the derivatives of secant and cosecant. So the derivative of secant x was secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. So when we take y prime for this particular function, we'll start with the 2 secant x, and its derivative would be 2 secant x tangent x minus the derivative of the cosecant x. That would be, again, negative cosecant x cotangent x. And so not a whole lot of simplifications here, just a matter of writing out what the derivatives are. We have the 2 secant x tangent x, and I'll just go ahead and write that as plus cosecant x cotangent x. This one, on the other hand, we do have to notice that we have y equals x squared sine x. This is a product of two terms. And so in this case, we have to use the product rule to take the derivative. So when we do that, y prime, we have to do the first x squared times the derivative of the second. Derivative of the second would be the derivative of sine x, which is cosine x. And we have to go plus the second times the derivative of the first. So the second being the sine x times the derivative of the first, which would just be 2x. So y prime is equal to x squared cosine x plus 2x sine x. Here we're going to look at the function y equals cosine x minus sine x and find the equation of the tangent line at the point pi comma negative 1. So to find the equation of any tangent line to any curve, we'll start with the derivative. The derivative y prime, we have to take the derivative of cosine, which was negative sine x, minus the derivative of sine, which is cosine x. And so for at pi comma negative 1, what we're going to use is x equal to pi and evaluate the derivative there. So y prime would be equal to negative sine pi minus cosine pi. Sine of pi was 0 minus the cosine of pi, which was negative 1. So in this case, we're just going to get a positive 1. And that's the slope of the tangent line. We take it then to the equation of the tangent line. So we'll be plugging in here y minus -1 equals 1 times x minus pi. So we go y plus 1 equals x minus pi. And y equals, we'll go y equals x minus pi minus 1. Here's some other functions. We're going to take a look at how we work the derivatives through with these. Starting with the function f of x is equal to sine x cosine x. In this case, we now have a function which is the product of two trig functions, here the sine and cosine. So we're going to have to apply the product rule to find the derivative here. So f prime of x is going to go first, which is sine x, times the derivative of the second, cosine x. That's negative sine x. And then from there we have to do the second, which is cosine x, times the derivative of the first. Derivative of sine x is cosine x. So our derivative f prime of x is going to be equal to negative sine squared x plus cosine squared x. If you call back to some of the identities for the trigonometric functions, this is almost similar to one identity that says sine squared x plus cosine squared x equals 1. But because that's a negative sine squared rather than positive, this doesn't match up with any identities that we have. So this is as far as we'll be able to simplify it. On this one, sine t over 1 plus tangent t. This is now the quotient of two expressions, and so we have a quotient rule that we have to use here. So we're going to be the high over the low. And so when I write down y prime, we'll go low, 1 plus tan t d high. Derivative of what's on top is cosine t minus high sine t d low. Derivative of the 1 plus tangent t. Derivative of 1 is 0, and the derivative of tangent, we look back in that secant squared t. All over the square of what's below. So the square of what's below would be 1 plus tan t all squared. Okay, this one I have some work to do in order to simplify it. What I'm going to do first is I'm going to go ahead and distribute this cosine t into the parentheses. We're going to rewrite it as cosine t plus tangent t cosine t minus sine t secant squared t, all over 1 plus tangent t all squared. Now, if possible, we're going to work in identities in order to simplify this further. Okay, and so what I'd like to do first is write everything, at least on top. I'm going to leave the denominator alone for now, in sine and cosine. I'd rather not mess with that denominator unless I absolutely have to, because it's all to squared and it's kind of not going to probably simplify too much. But I think we can do some stuff on top. So what that means is we're going to rewrite this as cosine t. Tangent t I can write as sine t over cosine t times cosine t minus sine t, and then for secant we can write that as 1 over cosine squared t. Now immediately something is going to simplify, and that's the cosine t. I can go ahead and cross that out. And so I'm going to rewrite this as cosine t plus sine t minus, not a whole lot going on simplifying in the other part with multiplying, but I will go ahead and just for a slight different way of rewriting it, make it into the sine t over cosine t times 1 over cosine t. Why I did it this way is I've taken the cosine squared and put it apart into two cosines multiplied together. That looks a little bit better because what I can do now is write this as cosine t plus sine t minus tangent t secant t. Nothing else can be really simplified at this point, since the denominator is all raised to the second power. Expanding that is not really going to go in any direction for simplifying. So this would be what our derivative would be. This one goes y equals x squared sine x tangent x. Okay, the overall picture of this one is we've got three different terms multiplied together. So it is a product rule. We will be using that as part of the taking the derivative here. However, we have two different product rules to apply, because we have the first term, which is a x squared, but then we have to consider the second for the product rule to be the sine x tangent x altogether. But then sine x tangent x is its own product rule situation that we're going to have to apply with its own first and its own second terms. So let's go through the process of setting this one up and taking the derivative. So first off, we're going to have y prime. By the product rule, we'll have the first, which is the x squared, times the derivative of the second. Now I'm going to write that as derivative of sine x tangent x. Then we have to do plus the second times the derivative of the first. Well, the second is the sine x tangent x times the derivative of the first. That would just be the 2x. Okay, so now once I've set it up this way, the sine x tangent x on its own will be its own product rule that we'll have to take the derivative of for that part of this derivative overall. So what it'll look like is x squared there, and then we'll start with the derivative of the sine x tangent x. That'll go first sine x times the derivative of the second, which is secant squared x, plus the second tangent x times the derivative of the first, which would be cosine x. Okay, and then we still have the other part here at the end, the 2x sine x tangent x. Okay, lots of things to do now at this point. Let's distribute this x squared here into the parentheses. So what we'll have then is x squared sine x secant squared x plus x squared tangent x cosine x plus 2x sine x tangent x. Now, not a whole lot of simplifying we can do, but there are a few things that'll happen if we go through and rewrite everything in sines and cosines. So for the secant squared, we'll change that over into cosine squared, 1 over cosine squared x. And then we'll have a sine x over cosine x for tangent. So that does allow us to reduce down one of these cosines here. That's good. At least we can simplify a little bit of this. I'll also go ahead and rewrite this as sine x over cosine x times 1 over cosine x. Then we'll have a plus x squared sine x plus 2x, and then really not a whole lot going on over here. So at the end here, we can write this as x squared tangent x secant x plus x squared sine x plus 2x sine x tangent x. On example 5, we're going to differentiate the function f of x equals secant x over tangent x and determine whether or where the graph of the function has horizontal tangent lines. Now, to do the derivative here, this will be the situation for a quotient rule. So we have to look at the high over low. So what we get here for f prime of x by the quotient rule would look like low 1 plus tan x d high. Derivative of secant is secant x tangent x minus high, which is the secant x, times the derivative of the low, which is secant squared x, all over the square of what's below. Now what I'm going to do next is multiply through the parentheses here and rewrite it. It'll look like secant x tangent x plus secant x tangent squared x minus secant cubed x over the denominator. Now what I'll do in order to try to get some simplifications going is there is a common factor of secant across all these terms. So let's go ahead and rewrite it and factor out that secant x. Then I'll make it look like secant x, and then in parentheses tangent x plus tangent squared x minus secant squared x, all over 1 plus tangent x all squared. Now the key thing we can do here is to apply some of our fundamental identities for trig. And the secant squared x had an identity in particular that would work good here. The identity said that secant squared x equals 1 plus tangent squared x. So I'm going to use that here in the place of secant squared x. So we're going to have secant x in parentheses tangent x plus tangent squared x. And putting it there, keeping in mind there's this negative here, so it's actually going to apply to the whole identity. We'll get negative 1 minus tangent squared x, all over 1 plus tangent x all squared. Now we can cross out the tangent squareds from the parentheses and rewrite it as secant x times tangent x minus 1 all over 1 plus tangent x all squared. And so this is the derivative f prime of x, all the way simplified. The question, on the other hand, though, asks for where the horizontal tangents occur. So where are the horizontal tangent lines? So that's going to be where the derivative f prime of x is equal to 0. So we're going to have to set 0 equals secant x, tangent x minus 1, all over 1 plus tangent x all squared. So technically when we're trying to solve this, we do need to reduce the denominator and solve with the numerator. So I can multiply both sides by 1 plus tangent x all squared to go ahead and reduce that. The other side is still going to stay 0. So we have 0 equals secant x, tangent x minus 1. Now, nicely, this thing is already factored out. So we can take each factor, the secant x, and set it equal to 0, and the tangent x minus 1. Set it equal to 0. Now if we try to solve the first one, I could rewrite it as 1 over cosine x equal to 0. Multiply both sides by cosine x. But all that's going to do is take away this cosine x. And One side will have a 1 and the other side will still be 0, which is a contradiction and means that there's no solution to that equation. On the other hand, this other one, we can write it as tangent x is equal to 1. And to solve from here, we can apply the tangent inverse. So that'll bring it down to x is equal to tangent inverse of 1. Tangent inverse of 1 in radian form is pi over 4. But with all solutions, that would be plus pi k. So this function, being that it's periodic, is going to have horizontal tangent lines at x equals pi over 4 plus pi k. Now, for example 6, we're going to be looking at a situation that says an object at the end of a vertical spring is stretched 4 centimeters beyond its resting position and released at time t equals 0. Its position at time t is s equals f of t equals 4 cosine t. Find the velocity and acceleration at time t, and we're going to use that to analyze how the object is in motion. So here's what we're looking at. This is a spring. It's stretched out 4 centimeters away from its resting position, which is indicated by 0 here. What will happen after it's been released is the spring will stretch back and go -4 up beyond on the other side of its resting position, or 4 centimeters on the other side of its resting position. That's going to be indicated by the -4. So we'll stretch it out to 4, then it'll snap back up to the other number above, which we call -4. And it'll do that oscillation for a little bit until it stops back at its resting position again. So here's one period for its oscillation from being stretched out to snapping back all the way and compressing the spring upward. So here's our function again, 4 cosine t. Here's where it's contracting. After being released, it contracts backwards, and then it goes past its resting position, which we call equilibrium, and it goes contracting all the way until it goes to what we were calling -4, where it hits the most compressed spot for the spring. And then it expands back out again as the spring begins to expand after being completely compressed all the way back out to 4. So if we consider the so-called equilibrium points where it passes its position at rest, let's look at the velocity function. Velocity is the derivative of the s of t function, so derivative of 4 cosine t is -4 sine t. Looking at its graph, this would be the graph of velocity. And we can see how the highest velocity, the fastest speed, in other words, happens at the points where it crosses its equilibrium resting location. Because in those points, it's in motion as it's compressing or expanding back outward, and so it's fastest right at those locations. For acceleration, we want to think about, okay, how fast is its speed increasing or decreasing? We can do that with the acceleration, which is derivative of velocity. So the derivative of -4 sine t is a of t equals -4 cosine t. And so the acceleration function, we can also make note of what's going on with it. The highest acceleration is happening where the spring is most compressed or where it's most expanded. So once it hits that moment where it's expanded the most or compressed the most, just after that point it'll start speeding up, and that's the fastest acceleration will be happening at those points.